In this lesson, what we're going to do is review some basic functions that are used a lot in computer science. Now, in a later lesson, we're going to talk about the complexity of different operations or algorithms when it comes to computing. But before we do, we need to review some functions that we're going to be covering in that lesson. Specifically, well, let's start out with the mod function or modulo. Any experience with that? We've already covered that a little bit. You've got this thing, how about m mod n? Sometimes it's written m mod n. Maybe you might see it with a percentage sign. But basically, what you're looking at is the remainder function, right? And so as a number increments, as this m increments, and let's go ahead and we can just put this on some sort of a xy axis. If you have m equal to 0, 0 divided by anything gives you a remainder of 0, all right? As long as n is greater than whatever we're dividing it into. In other words, we're doing some sort of a m divided by n generates a remainder, all right? As long as m is less than n, then no matter what the value of m is, if it's less than n, it is going to always be exactly equal to the remainder. For example, 4 divided by 5 gives you a remainder of 4, all right? And so every time you increment m, you're going to get to a larger, that exactly the same value in terms of the remainder. As soon as m equals n, then you've got m divided by n is equal to 1 with a remainder of 0. And so this goes back down to 0. Now you continue to increment m, and it gives you incrementally larger values of the remainder until m equals the next multiple of n, and then this goes back down to 0. And so what you end up getting is this sawtooth wave. I'm an engineer, and that's what it looks like to me, is this sawtooth wave. Now, whenever it comes to negative numbers, it does that same pattern. And this may not make a lot of sense, but for example, at -1, then the remainder, you're looking at a positive value. You're not looking, the remainder always is going to be positive. Remember, we're working with that formula, m is equal to some sort of a q times n plus r, where r is greater than or equal to 0, but less than n. All right, and so that's exactly what the remainder function looks like. So this, when we go to -1, we hop back up here and continue doing this sawtooth wave in the reverse direction. So as soon as you go to -1, then the remainder function is going to give you n minus 1, or that next integer down from n. Now, the next function we talked a lot about whenever we were doing the counting, right? We had this thing called a factorial, and it was represented by some n with an exclamation point. And basically, all it was 1 times 2 times 3 times 4, all the way up until you got to n. Now, the factorial is really important whenever we're doing this idea of complexity, because this particular expression really explodes whenever you get to larger values of n. And when you're talking about complexity, you don't want your complexity to explode as you get to larger values. So we need to be able to address, or at least recognize, this particular function. The next function, which we also talked about, was the floor function. Now, the floor function was represented, if we had some sort of f of x is equal to, well, it was represented with these weird little L shapes, right? And it showed what is the largest integer that is less than or equal to x. So for x is equal to, let's just say 3.00001, the floor function of x is equal to 3. It works with negatives too. So if you have x is equal to -5. How about 9824? Then the floor function of x, what's the largest integer that is less than -5.982? Well, that's -6, okay? And the expression you get, or the graph you get, is this weird stair step. Let me show it to you. Now, if you look at this stair step, you'll see that there is a closed dot representing that particular integer exists in that line, and then you've got the open circle. The open circle says that particular integer, no, you're going to find it in the next level. So as you've got, for example, in this graph, you're going from -4 until you get to 3, and it jumps up, it steps. And then you get to -2, and then you get to -1, and so forth. And that's the stair-step function. Now, the ceiling function, a lot like the floor function, what you're looking at is f of x, and you've got the upside down L's this time. And what you're looking at is the smallest integer that is greater than x, all right? So if I've got x is equal to 1.25, then the ceiling of x is equal to 2. All right, works with negatives again. So you have x is equal to negative, how about 5.39? Then the ceiling function is the smallest integer that is just greater than -5, which is equal to -5, excuse me, just greater than or equal to -5.39. And so the ceiling function is going to equal -5. Now, the graph that we get from this guy, well, it's also a stair step, but it's shifted over. It's shifted over to the left so that now anything, for example, if you've got anything that is between 0 and -1, well, anything that is just above -1 all the way up to 0, its ceiling is 0. Then you hit 0, that the ceiling of 0, the ceiling of an integer is equal to its integer, right? And that's true for the floor function too. The floor of an integer is equal to the integer itself. So whenever you go to 0, that's the ceiling is 0. But as soon as you get just above it, you go up to 1. Now, it turns out that the factorial is not the only function that grows so tremendously for larger values of n. There are things like squared, right? So you have f of x is equal to, we'll just say x squared, or f of x is equal to x cubed. We've got these exponential functions, right? But there's also a function that grows tremendously, and that one is f of x is equal to some sort of a constant, we'll just say 2 in this case, to the x. Have you ever heard of that, well, kind of riddle that says, what if you had a piece of paper and you folded it in half, and then you folded it in half again, and then you folded it in half again, and then you folded it in half again, and you did this 42 times. Not a very big number, just 42 times. How tall, every time you double it, then you increase the height of this piece of paper. Well, let's assume that paper has a thickness of 0.004 inches. So it's pretty thin, right? How tall would the stack be after you doubled it 42 times? Well, if you double it 42 times, that's 0.004 times 2 to the 42. Well, that is equal to 17,592,186,044 inches. What does that equal to in miles? Well, it turns out in miles, that's 277,654 miles. You know how far it is to the moon from the Earth? Well, if from the moon to the Earth, it is 238,900 miles. So it turns out that if you fold a piece of paper, if you can, in half 42 times, its stack will actually go past the moon. So we can look at this table here that shows for different values of x what 2 to the x is equal to. And you can see that we've got 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, but then you get up to 2 to the 10. 2 to the 10, that's 1,024. That's 1K. 2 to the 20th, that's over a million. So you've got 2 to the 20, that's usually referred to as a meg. You go up to 2 to the 30th, that's a gig, or over a billion. But then you also go to the negatives, and as you go to the negatives, you'll notice that it never equals 0, but it gets darn close. Now we've got another very important function that we are going to take a look at, and that's the logarithm. Now, for those of us that are a little bit older, we actually had tables in the back of our mathematics books. These tables gave you the log of different values, the logarithm of different values. Now, the reason we did that was because we used it in order to do complex arithmetic, complex multiplications or divisions, because of the characteristics of the logarithm. Now, the way the logarithm works, if you've got something like log base a of x, what that's saying is that a to the what equals x. So a to the question mark equals x. And what you're solving for is the question mark. Well, if you're familiar with exponential operations at all, you'll know that something, for example, a to the 5 times a to the 6 is equal to a to the 11, a 5 plus 6, right? And then a of the, we'll just say 7 divided by a to the 3rd, that's equal to a to the 7 minus 3, which is equal to a to the 4th. And so this idea of being able to understand what exponent to raise a to in order to get a particular value can actually be used really quickly to do operations with the logarithm. So for example, if I have the log of a of, we'll just say, x times y, that's the same thing as the log base a of x plus the log base a of y. And if we're doing this in terms of division, the log base a of x divided by y, that's just equal to the log base a of x minus the log base a of y. Now there are a couple that we're not going to worry about. For example, the log of any base of 0 doesn't exist. So we're not going to worry about it. And when it comes to things like the log of negative numbers, we're also not going to worry about that because they usually represent complex numbers beyond the scope of what this lesson is going to cover. Now, there are some very common logarithms that we'll use. For example, one of them, the binary logarithm, well, that's just log base 2. And the way that is usually represented is just LG of x. Another common one is the decimal logarithm. So in decimal, we have log base 10 of x. Typically, that is represented with just log of x. So if you look at the buttons on your calculator, this is typically the way that it's represented. And then you also have the natural logarithm. And that one is using the constant e. What is it, 2.7812? Anyway, look it up. And that one is usually represented with ln of x. Let's do a couple of examples with a binary logarithm. Let's say, for example, that I have some sort of a system that takes on, I don't know, let's just pick a number. How about 496 different states or conditions? What I need to do is represent and use a unique number, a different number to represent each one of those states so that the system, all it has to do is look at that number to know which one of those states or conditions it's in. Now, let's also say that I'm limited in terms of the amount of memory I've got to store this. So I want to know what is the minimum number of bits, binary digits, right, in order to represent 496 states. All right. Now, it turns out that we're going to use the binary logarithm in order to solve this, because by figuring out what power of 2 it represents 496. In other words, log of 496 equals whatever. We will find out what power. So 2 to the what equals 496, we'll figure out exactly what the minimum is in order to represent 496. And in order to make this a little bit more mathematically correct, we are going to figure out what the ceiling is, because we can't use half a bit. We have to use a whole bit. So if any portion of a bit that's required in order to represent 496 is going to require one full bit, so we use the ceiling function. Well, the ceiling of log 496, well, log of 496 is 8.95419631, and the ceiling of that is equal to 9. Now, is that right? Well, think about it this way. 8 bits can represent values from 0 to 255. So 255, that doesn't quite make it. 9 bits can represent values from 0 up to 511. That just covers our 496 different cases. Let's do another example. This table right here shows you the different frequencies for the different notes of A. All right, so the very lowest A on the keyboard is 27.5 hertz. All right, now we go one octave up to the next A, and that's 2 times 27.5, or 55 hertz. We double that again to go up to A2, and that gives us what? 110 hertz. Double that again, 220, double that again, you get to the middle A, 440. So maybe what I'm doing is I've got an A and another A, and I know they're both A's, but I want to know how many octaves separate them. Well, it turns out that the number of octaves, all right, in other words, the number of octaves that separate this particular A from another particular A, well, that's just log base 2 of the one A, and we'll just call this A sub n, over the other A, and we'll call that A sub m. And let's say that I've got, I don't know, we want to know what the number of octaves between, how about A7 and A4? Okay, and that's going to be equal to the binary log of 3520 over 440, and you divide 440 into 3520, and you're going to get 8. The log of 8, well, 2 to the what equals 8. 2 to the 3 equals 8, and you realize that these two frequencies are 8 octaves apart. Let's do one more example. Let's say that we have a tennis tournament and we have 58 players that have signed up. And these 58 players are going to go through different layers of a single elimination tournament. How many layers do we need to go through? Well, 58 is not a power of 2, but we can still use logarithms in order to figure out how many different layers we've got. Because what's going to happen is you're going to have something like a single winner, right? And that single winner is going to come from the match of 2 players who were decided with 2 games of 4 players who were decided with 4 games of 8 players, and so forth. How far do we have to go back in order to get to 58 players? Well, it turns out that it's a pretty simple operation of the base 2 logarithm of 58. And then we have to do the ceiling function again, because remember, we can't have we have to have an integer number of levels. And so some of the players are going to get byes. Let's go ahead and figure out which ones they are. But before we do, let's figure out what the logarithm of 58 is and figure out what the ceiling is. So the ceiling of the log of 58 is equal to the ceiling of 5.857 9, 8, and some digits. We actually only needed to go to the first digit, right? Because we just need to know it's 5 point something. Well, that's equal to 6. The ceiling of 5.8 is equal to 6, telling us that we have to have 6 levels to our match. Is this right? Well, think about it this way. If I have 58 players, then they are going to play 29 games in order to figure out the 29 winners of these games. Well, once you get the 29 games, then you're going to divide this also in half. And what this is going to give you is, well, 14.5, right? Well, that 0.5 is not really what we're looking at. What we're looking at is a remainder of 1. And that remainder, that's the one person that got a bye in this second level. Now, that means you have 14 winners of 14 games plus the one person who got a bye. That's 15. Divide that guy by 2, and what you get is 7 with a remainder of 1. 7 winners plus the one who got a bye. That gives us 8 people that's left. 8 divided by 2, that's 4 winners. Then you have 4 divided by 2. That's going to give us 2 winners. And then you have 2 divided by 2. That will give you your final winner. Was that 6 levels? 1, 2, 3, 4, 5, 6. Yes, we had 2 different levels that had byes, but there you go. There's your 6 layers. Now, there are a couple other things about logarithms that we need to make sure we cover. Now, a couple of other things. If you look on your calculator, you'll know that you more than likely don't even have a binary logarithm. You do have a base 10 logarithm, the log. You might have the natural logarithm, ln. But what's really cool is that to go between the different logarithms, it's really just about multiplying by a constant. And so if I have the log of A, log base A of B, that's really just equal to a simple division. What it gives us is the log base C of B divided by the log base C of A. And so whenever we're trying to look at the ratio of the log of B for one base to the log of B to another base, it's just multiplied by a constant, this 1 over log base C of A. And that's all it takes in order to convert from one logarithm to the other one. And then we have the basic functions that we've already talked about. Log of n to the k is just equal to k times log of n, and log of n times m is just equal to the log of n plus the log of m. And then we have the log of n divided by m is just equal to the log of n minus the log of m. So, if you have a good grasp of these different functions, we will have no problem whenever we move on to our discussion about complexity of these different algorithms in computing.